In this video, we shall discuss how to handle some typical specifications while designing controllers. In particular, we'll learn how to make sure that output of the plant doesn't go beyond limits and reaches the desired response within specified time. Here is a typical feedback block diagram. We are given a plant G and sensor H. We're given the reference command R, the disturbance T comes uninvited, and we get the output Y. The main aim of the control system is that given the plant G of S and sensor H of S, you must design the controller K of S and if needed the prefilter F of S so that output Y as a function of time follows the reference command R as a function of time. But this may not be easy, so let's start simple. The simplest thing we can ask for is stability. Stability basically means that Y of t doesn't go to infinity for bounded or finite R of t. For stability, we want the poles of the closed loop system, which are the poles of the transfer function from R to Y, to have negative real parts, i.e. we want them to be to the left of imaginary axis. We want closed loop poles in the left half plane. The next thing we can hope for is that even though Y of t may not be equal to R of t at all the times, but at least eventually it should follow it. We call this goal as the low steady state error. Consider this graph. Let's say the red curve is Y of t, and let's say the green dashed line is the R of t. The Y of t starts from 0, but at least eventually it should come close to R of t. The error E is the reference R minus the output Y, and we want this to be small. This low error specification typically boils down to constraints on the DC gain of the controller, or having 1 over S in the controller, i.e. having integrators in the controller. Finally, even though we want Y of t to eventually follow R of t, we may have some other specifications on the way, and we call these the transient specifications. The gist of these specifications is that Y of t doesn't go too far beyond R of t, and it stays within limits. The examples of these specifications are 2% settling time. It is defined as a time taken by Y of t to reach within plus or minus 2% of the steady state value. Another example of the transient specification is the overshoot. It is defined as the maximum amount in percentage that Y of t ventures away from its steady state value. We can see the settling time and overshoot in this graph. Other specifications include the effect of reducing the effect of disturbances on the plant output Y and making sure that the controller doesn't request too much U of t to be given to the plant. Let's talk about settling time and overshoot specifications in some more detail. You provide in the reference command R as a function of time, and eventually you get the output Y as a function of time. If we can find the function Y of t, from that we can calculate what steady state value it reaches, how long it takes to settle within 2% of that steady state value, and how much it overshoots beyond that steady state value. The best way is to first find out the Laplace version of Y of t, that is find Y of s, and then Y of t is just the Laplace inverse of Y of s. Consider the block diagram shown on the side, which has two overall inputs R and D. Ignoring the initial conditions, the output Y of s can be written as y is equal to transfer function from R to Y times R plus transfer function from D to Y times R. Note, we can get all this quite simply by using the Mason's rule. The transfer function from R to Y is the forward path from R to Y, which is fgk or fkg divided by 1 plus the loop transfer function gkh. The transfer function from D to Y is a forward path from D to Y, which is just g divided by 1 plus the loop transfer function gkh. Now for a moment, if we just ignore the effect of disturbance and just consider the R, the whole block diagram can be simplified into a single block whose input is R and the output is Y. And the transfer function from R to Y, i.e. the closed loop transfer function, is fgk over 1 plus gkh. If the reference command R of t is a constant, i.e. that the reference command is just a step function, then Y of t is just a step response of the closed loop transfer function. And from this response function Y of t, we can calculate settling time and overshoot and other transient specifications. In particular, if it so happens that the closed loop transfer function is a first order system written in the DC gain format as KDC by S tau plus 1, then we already have these formulae. Settling time is 4 divided by magnitude of the pole, which is 4 times tau, and the overshoot is just 0. If it so happens that the closed loop transfer function is a second order system written in the format as shown, then also we already have the settling time and the overshoot formula. The settling time is still approximately 4 divided by a real part of the pole, and overshoot depends on the damping ratio zeta alone as per the formula shown. These formulae for first and second order system response are only for step inputs, and they are very important and one must remember them. Let's discuss them in more detail. If we ignore the disturbance and just consider the reference command, the overall system once again could be reduced to a single block with a closed loop transfer function inside it. Now let's look into the formula for settling time and overshoot in a little bit more detail if the closed loop transfer function is a first order system written as such. The pole of the system from the denominator polynomial is just minus 1 over tau. There are no zeros in the system, and the DC gain of the system is KDC obtained by plugging S equal to 0 in the transfer function. We can draw the pole zero diagram of the system. There would be no zeros, just one pole, and the pole would be at the location minus 1 over tau. If you give in a step reference command, so it would start from 0 and suddenly become equal to a value, say x, and stays at x forever, then y is going to start from 0 and eventually reach a constant value. The steady state value of the y steady state, is going to be the DC gain KDC multiplied by the reference command value, which is x. The time taken for you to go from 0 to 98% of the steady state value, i.e. within 2% of the steady state value, that would be called the settling time, TS. And the approximate formula for settling time is 4 divided by magnitude of the pole, which is 4 times tau. The overshoot is how far you go beyond the steady state value, and then you didn't go beyond the steady state value at all, so the overshoot is 0. If you assume the closed loop system is a second order system shown in the following format, then this system has two poles, and by looking at the denominator polynomial and solving using quadratic formula, we can find the poles as minus zeta omega n plus or minus I omega n times 1 minus zeta square root. This is assuming the system is underdamped, which means zeta is between 0 and 1. In that case, the poles are complex with real and imaginary part. There are no zeros in the system, and the DC gain of the system obtained by plugging S equal to 0 in the transfer function would be just KDC. We can draw the pole zero diagram of the system. The system, assuming once again underdamped system, will have two poles which are complex conjugates. They will have a real part which is minus zeta omega n. They will have an imaginary part which is omega n times square root of 1 minus zeta squared. If you connect the pole to origin by a line, then this would be called the angle of the pole. Let's represent that by a symbol beta. If you give a step reference command which starts from 0 and suddenly reaches a constant value x, then the output y is going to start from 0 with 0 slope, oscillate a little bit, and reach a constant value. This constant value, y steady state, is going to be DC gain multiplied by the value of reference command, which is x. Settling time is defined as time taken to go from 0 to within 2% of the steady state value. That is TS. And the TS formula is just like the first order system, 4 divided by the magnitude of the real part of the pole, which is 4 over zeta omega n. Overshoot is how far you go beyond the settling time. And the overshoot only depends upon the angle of the pole. So it's e to the power minus pi cotangent of the angle of the pole. Now it could be shown by some math that the angle of the pole is related only and only to the damping ratio. The relation is cosine of the angle of the pole is zeta. Using that, we can convert this formula into a corresponding formula only involving the damping ratio. One must remember the definition of overshoot. Overshoot is defined as the maximum value of the y, which is how far it goes from the steady state, minus the steady state divided by the steady state. So it's what fraction of steady state value did you overshoot by. If you multiply this formula by 100, you get the percentage overshoot. There is yet another kind of transient specification. It's called as peak time. Peak time is defined as time taken to go from 0 to the maximum value, so this time. And peak time is 4 divided by the imaginary part of the pole, so it's going to be 4 divided by omega n square root of 1 minus theta squared. There is yet another specification. We call that as the rise time. It's defined variously. We can define this as time taken to go from 0 to the 100% of steady state for the first time, or some people define as time taken to go from 10% to 90% of the steady state value. It's a complicated formula, and then it's not very relevant to remember its formula, but its definition is useful. Now, it may not always happen that the closed loop transfer function is a second order system or a first order system. In that case, we are not going to derive settling time and overshoot formulae for all possible systems. That's a waste of time. Instead, we will hope that we can approximate our higher order system by simpler first and second order, and then use the first and second order formula. So that's the idea behind using dominant poles. So let's assume you have a complicated system. It has many poles and perhaps zeros, but there is one pole which is clearly closer to the imaginary axis than the others. Then we can ignore these, and this system is approximately a first order system. Similarly, if you had a system with many poles and there were two clear poles which were closer to the imaginary axis, then we can just ignore all the left things and just keep the two most dominant, and then we can approximate that as a second order system. So that's the first idea, that we can ignore poles and zeros which are far to the left. Other option for us is assuming if we have one pole and there's a zero nearby, then we can cancel their effect, and those are also not dominant. So this system with many poles and zeros could still be approximated as a first order system because only one pole is the most dominant one. And we can just use a lower order formula to handle this higher order systems. Now that may not always happen. Sometimes we will have extra zeros in the system. In that case, one must understand what happens if you have poles and then if you have a zero nearby which cannot be ignored. Then the effect of zero is that it can increase overshoot if there is any, and zeros make the system go faster, so they decrease the settling time and they decrease the rise time and the peak time. So whatever a second order formula will predict, the effect of zero is going to give you higher than that formula overshoot and lower than that formula settling time and peak time and rise time. If you have extra poles in the system which are nearby and not non-dominant, then those extra poles have exactly the opposite effect of zeros, which means they tend to decrease the overshoot and they tend to increase the settling time. Hence, using this idea, we can approximate the higher order systems by first order and second order formulae, but always remember the effects of extra poles and zeros. Let's relate back all these formulae for settling time and overshoot back to the specifications. We're going to take a sample case where the closed loop transfer function is an underdamped second order system because we just have the formula for it. Let's say one of your specification is that the output y of s has settling time less than 2 seconds, which means the response y should reach the steady state value for within 2% of the steady state value in less than 2 seconds. If you use this formula, 4 over the magnitude of the real part of the pole is less than 2, and rearrange this a little bit, that means the magnitude of the real part of the pole should be larger than 2. This means that if you want the settling time to be less than 2 seconds, the pole's real part should be more negative than -2. That means the magnitude is larger than 2. So the pole has to be in this region to the left of -2 line. Similarly, if you have a requirement for overshoot, let's say you want the overshoot in the output to be less than 10%, then using this formula, MP being less than 10%. 10% is, by the way, 10 divided by 100, so 0.1. So if you want MP to be less than 0.1, this will boil down to some relationship of angle being less than some number. I don't know, let's call it 45 degrees. It's not really true, but still. So the overshoot being less than a particular value boils down to angle of the pole being less than a particular number, and the region corresponding to that would look like this. So your closed loop poles should be in this region, and the angle of the pole would always be less than the beta you calculate. And having the closed loop poles for the second order system in this region will give you the right overshoot. If you have a specification on the peak time, let's say you want the peak time to be less than pi seconds. So in that case, by rearranging this formula, you basically get that the magnitude of the imaginary part of the pole should be larger than 1. That means the poles, closed loop poles, should lie in this region. Imagine two horizontal lines at +1 and -1 imaginary parts. So if the pole lies in this region, their imaginary parts would have larger than 1 magnitude, and they would follow the peak time requirements. So the main interesting point over here is this, that all the settling time, overshoot, and peak time requirements boil down to closed loop poles being in some special regions of the S-plane. Now this is only for second order system, all these formulae. If you have a higher order system, then we're going to shamelessly use the second order formulae as guidelines, but we must still remember that whatever these second order formulae predict as the regions for the poles to be, we have to take that with a grain of salt and consider the effect of extra zeros and poles. Now, to summarize all this, we have a closed loop system. In that closed loop system, we are given the plant and we're given the sensor. We want to design the controller and possibly the pre-filter. But we have to design for given specifications of the output Y in mind. The stability specification means the closed loop poles, the poles of FGK over 1 plus GKH, should be in the left half plane. Error specification typically boils down to something about the DC gain of the controller. And settling time and overshoot specifications, as we just saw, boil down to us having the closed loop poles in some special regions. So in that controller design process, the location of the closed loop poles really matters. And we need to find a way so that we can find the location of closed loop poles as we try out different pre-filters or try out different controllers and adjust their gains. And that mathematical technique which tell us how the closed loop poles of a system move around or change as you adjust the gain of the controller or choose different controllers, that's called root locus, and we shall see that in future.